Hi, my name is Shashwati. I'm a senior at South Dakota School of Mines and Technology, majoring in mathematics and computer science. In this presentation, I'm going to talk about my research with Dr. Cottle and Dr. Hoover on advanced decision-making and interpretability through neural shrubs. For our research, we were interested in two machine learning models, neural networks and decision trees. Neural networks have a wide range of applications from computer vision, speech recognition, and self-driving cars. They are used to recognize complex patterns in data. Decision trees are a hierarchical structure used for making decisions using a sequence of yes and no questions. While both neural networks and decision trees can detect nonlinearity and handle interactions between variables, decision trees are more interpretable and faster to train. However, neural networks have higher accuracy and can detect complex patterns, but they behave like a black box, and its training time is comparatively very high. So our research question was, can we improve the interpretability and training time of a neural network without sacrificing its accuracy? We started by understanding how decision trees work. Decision trees divide the space into rectangular regions. In this example, we can see that if x is less than -1, or x is greater than 1, or y is less than -1, or y is greater than 1, then the predicted class will be class 1. Otherwise, it's class 2. To improve the performance of the decision tree, we added neural network to the leaf node and ran the data from the decision tree followed by the neural network to get our results. So far, our work was similar to what was done in the past. For our neural shrub algorithm, we partitioned the space using a decision tree like we did in the previous algorithm. However, this time, we took the leaf nodes, which were predicted to be in the same class, together and trained a neural network on them. The advantage of this technique was that it reduced the number of neural shrubs from the total number of leaf nodes to just the number of classes, and also provided more data for the neural networks to be trained on. To evaluate the decision tree, we built 4 models for each dataset. If it was a classification dataset, we built a confusion matrix for each model. We evaluated the models using precision, recall, F1 measure, and accuracy. If the precision and recall were similar, we used accuracy to pick the best model. Otherwise, we used F1 measure. For regression dataset, we simply used the mean absolute error to pick the best model. The training time for the neural shrub was calculated as the sum of the time taken by the decision tree plus the maximum time taken by a neural network, assuming it can be done in parallel. We started with the MNIST dataset. The goal was to classify handwritten digits into the correct digits. Since the precision and recall were similar, we used accuracy to pick the best model. We found that the neural networks outperformed the neural shrubs. However, the training time for neural shrubs was way smaller. In the Connect 4 dataset, we wanted to predict who will win the game based on the position of the pieces. Since the precision and recall are imbalanced, we used F1 measure to pick the best model. Neural shrubs on classes outperformed neural networks and neural shrubs on leaves. For regression, we picked the Million Song dataset, in which we wanted to predict the year in which the song was released using its audio features. Since regression datasets don't have classes, we only used neural shrubs on leaves. On an average, the songs were off by 6 to 7 years, but the training time for the neural shrubs was still very low. From our study, we showed that the neural shrubs improved the accuracy of the decision tree drastically with a relatively shorter training time. However, This technique still required large data sets, and the classification rate was still lower than a standard neural network. We also realized that the depth of the tree directly affected the training time and the accuracy. Some of our future work include examining the leaf node topology to bound the total data needed by the neural network. We also want to investigate automatic pruning of the depth of the neural shrub rather than using traditional cross-validation methods. The benefit of a neural shrub would be that it would rapidly help in evaluating neural network architectures, do more hyperparameter optimizations, and improve interpretability so that we just don't know the predictions, but also know how to get them. Thank you.